try to understand the switches. Okay, so let us start. Today's lecture 9, right?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay, lecture 9. And date is 9. Okay, so first you need to understand the switch. After that, we can understand in the gates using CMOS. So CMOS transistors basically acts as a switch, right? So first, let us try to understand three circuits. Let us see here, we are connecting the circuits in such a way that here in the LED is connected. Okay, so let us see here. This is a V, this is R, and this is LED. Okay, so conditions. Let us say if switch S is closed. So S is closed, then what do you think about the LED? LED will glow or not?
Will not glow.
Will not glow, right? So here closed means 1. Okay, what will happen if the switch S is open, means logic 0, then in that case LED will glow, right? So why it is happening like that? If the switch will be closed, it means that this branch will be short. So all the current, total current will pass through this short, and this will not pass through this LED. So in that case, this LED will not glow. When the switch will be open, then in that case, the current will not pass through this branch. The current will only pass through the LED. Then in that case, it will glow. So now the second circuit. So here it is okay. Now discuss. So we can consider this circuit as a, for example, you can say NOT gate. Now, what will happen if you connect the switches in parallel to any circuits? So let us see here. Okay, we have to connect the switches in parallel. This is the symbol of switch. So let us say this is S1, S2, and here the resistor is connected and it is LED is connected. So now we have to guess here, let us say this is V. Okay, so what will happen if S1 will be closed and S2 will be open?
LED will glow.
LED will glow, right? This is LED. So LED in this case will glow. Okay, let us say S1 open and S2 closed. Then in that case, S1 is open and S2 is closed. So in that case, what will happen to the LED?
So LED will glow.
Will glow. Now, if let us say both the switches are closed, both S1 and S2 are closed. In that case also LED will glow, right? So now we have to take, let us say both the switches are open, are oh, are open. Then in that case, what will happen? Current will not flow through the LED. So LED will not glow. So here we have to first of all understand closed means logic 1 and open means logic 0. So can we consider this type of configuration as a OR gate? Yes. So this type of circuit, this type of configuration of switches, we may consider it for OR gate. Okay. So for the OR gate, what is happening? All the switches are connected in parallel, right? Okay. Let us talk about the third case, that is here. Here the switches are connected in series now. So what will happen? Let us say this is S1 and S2. V1, sorry, V, R and LED. So just make a configuration S1, S2 and LED. In this way you can understand. So let us say this is, okay, open. So what will happen in that case? If switch S1 and S2 both are open in that case to the LED? Yes?
Will not glow.
Will not glow. Okay. What about this is, let us say this is open and this is closed. So what will happen in that case? Again, it will not
glow.
Now S1 is closed and S2 is open. Again, it will not glow, right? Because circuit is not completing. Now both the switches are closed. Switches are closed. It means that will glow. Okay, so what we can conclude from these three cases, if we are interested in designing the AND gate OR gate, then we have to connect. Let us say for example for OR gate, if we are interested in designing the OR gate using CMOS, then we will have to connect the CMOS transistors in parallel, right? However, if we are interested in designing the AND gate, then we will have to connect the CMOS transistors in series. Okay, so this is the conclusion from these three cases. So now we will move to our topic, that is combinational logics. Okay, so here, so in the last lecture we have already seen the truth table and symbols for the OR gate and AND gate. So combination logics. So it performs Boolean operations on multiple input variable and determine the output as Boolean functions of the input. Let us say for OR gate. For OR gate, if we talk about, so what are the output or what are the Boolean expressions for, let us say Y is the output and A and B are the inputs. Then what will be the Boolean expressions for OR gate? Yes. Let us say A and B are the inputs and Y is the output for OR gate. Then what will be the Boolean expressions for OR gate? Do you remember? It will be Y plus Y is equal to A plus B. Similarly, for if we talk about the AND gate, for two inputs AND gate, so let us say the expression will be Y is equal to Y is equal to AB. So it performs combination logics, performs Boolean operations on multiple input variables and determine the output as Boolean functions of the inputs. So the basic two input and OR functions can be realized by series and parallel combinations of NMOS and PMOS transistors, as we can see. So we know very well to design the, let us focus on the first OR gate. So if we are interested in designing the OR gate, we using CMOS transistors. So we know very well about the CMOS transistors. CMOS transistors transistors can act as a switch. So if we are interested in designing the OR gate using CMOS transistors, then we will have to connect the CMOS transistor either in parallel or series. Yes? What will be the configurations for OR gate? It will be in parallel, right?
Parallel, sir.
Yes. So let us talk about the NMOS first. Let us consider NMOS, using NMOS. Okay. So if you are interested in designing the OR gate using NMOS, then we will have to connect the switches, that is NMOS transistors, in parallel. Okay. So let us talk about the parallel. So what can be the possible parallel configurations? See here. So in this way, you can design or you can connect the various transistors in parallel. Okay, so we are interested in designing the gates using two inputs OR gates, right? So two inputs means here, let us say this is the first input, that is A, and second input, that is B, and here the input signal, that is, let us say N1 for the transistor 1, this is a gate signal exactly, and this is N2. So if you are interested in designing the OR gate using PMOS, then the configuration will remain the same, but only the representation of transistors will be different. So I will let you know the operations. Okay, this is A, B, N1, and N2. Okay, so now we will understand the operations of this OR gate. Okay, so what will happen? A two input OR function, which means that here the appearance of same voltage in A and B, that is A and B, where, let us see, first we need to understand what is where A and B are the input variables for two input logic gates, OR gate you can say here, and where N1 and N2 are the gate signal, Okay. Okay, so we know very well for this is NMOS. So for NMOS, what will be the range of N1 and N2 to operate the transistor? It should be less than 0 or greater than 0 for NMOS.
Greater than 0.
Greater than 0, right? For NMOS. So greater than 0, here we are talking in terms of logical, right? So it means that it should be 1, right? It should be logic 1. Means this is greater than 0. What about the PMOS? For PMOS, N1 and N2 should be less than 0 or 0, you can say. So it means that this is at logic 0. So in the last lecture, we have discussed about the logic 0 and logic 1. So 0 voltage considered as, roughly you can say, 0 voltage is considered as the logic 0 and 5 volt is considered as a logic 1. So here we will try to understand what will happen if, let us talk about the operations here. So for, let us say here, you are applying the logic 1 at this gate, and let us say this combination is 0, 0. Okay, let us make a truth table first here. A, B, and output, that is, okay. So let us say configuration first, 0, 0, 0, 1, 1, 0, and 1, 1. So we will try to understand. What will happen if both the inputs of this configuration is 0? Then you will get output signal. If the VDD and VSS signal are 0, then in that case you will get the output. This is known as The input here, A and B are the inputs. You can say here, you can consider here as a VDD signal. So what will happen for the VDD 0 and VSS 0? Your transistor will work. This is MOS 1, and you can say here the MOS 2. Let us say NMOS and NMOS 2. So what will happen if your gate signal is already applied, that is at logic 1, and you are supplying the voltage that is A and B, that is 0, 0. So in that case, what will happen? Both the transistors will be off. Okay, not exactly the here, just right. Okay, then you can understand in detail. Let us say NMOS 1, NMOS 2, and then here you can say output. Okay, so what will happen? If the A will be 0 and B will be 0, then in that case, what will happen to the transistors? It will operate or not? Which transistor will operate and which transistor will be off? So for 0, 0, what will happen? Both the transistors will be off. Okay. For 0, 1, 0, 1 means here what is happening? 0 and 1 means A is 0 and B is 1. Then in that case, what will happen? This transistors NMOS 1 will be off. However, NMOS 2 will be on. Similarly for the A is equal to 1 and B is equal to 0, then in that case, it will be on and it will be off. And for both at the logic 1, then both the transistors will be on. So what will happen to the output? If both the transistors will be off, then you will not get current or voltage in the output. So it will be 0. What will happen to the 0 and 1? That is, here you can see one transistor is off and another transistor is on. So in that case, you will get something in the output, because transistors are, both the switches are connected in parallel. So if one switch is off, that is switched off, it is not connected, not closed, means open here, and another switch is closed, then in that case you will get output.
Sir, sorry to interrupt. So what is where are we taking the output from?
Where you are getting the output? Let us say from here. Because all are sorted, right? Both the switches are connected and sorted. So what will happen to the output? Just you have to correlate with this term, this switches, this configurations. Let us say this switch S1 is closed and S2 is open. Then in that case, you will get output in the circuit. If anyone is closed, then in that case, you will get the output, right?
Yes, sir.
Right? So what will happen? Let us say for these configurations, parallel configurations, you will get output here. Let us say this is logic at 1, 1, and 1. Because the switches are, that is transistors are connected in parallel. So because of the parallel, we know very well the voltage remains same. Let us say about the circuit here. If I will ask you R1, R2, let us say this is V, and here V output. So what will the V output? Can you guess here? Yes? For the parallel combination, because this is all the resistors and voltage source are connected in parallel. Then what will be the V out here?
V.
V. Let us say here, due to any reason, R2 has been replaced or it has been burnt, you can see. Then again, I will ask, what will be the V output here?
Same V.
Same V, right? try to configure another possibilities that R1 is burnt, and here we are interested in finding the V out. Again, you will get the same voltage, right? So whenever the two transistors or two switches are connected in parallel, and if any one of the switches is closed, then in that case you will get something in the output. Okay. Okay. So what are the necessary condition for the NMOS for the logic for the OR gate? If you are designing the OR gate using the NMOS CMOS transistors, so what will be the necessary conditions? The necessary condition is that the input signal, that is N1 and N2, N1 and N2 must be at logic 1. Logic 1. Similarly, for the PMOS, what will be the necessary conditions? N1 and N2 must be at logic 0. Okay, so any doubt in understanding this concept?
No, sir.
Okay, now move to the second case, that is AND gate. So we know that for the AND gate, the switches are connected in series, right? As for this circuit, if you see this circuit, so to design the AND gate, we will have to connect the two transistors in series. Either the type of the transistor will be P type or N type. It is not going to affect your result. The concept will remain the same. So let us say using first case, using NMOS. Okay. So okay, based on this, if I will ask you in the exam, if I ask you to design the OR gate using the PMOS transistors for 3 input OR gate, so what will be the number of transistors? How much transistors you need to connect in parallel for 3 input? Yes,
Sir, 3.
3. So just you have to keep in mind. And what will be the necessary conditions for the PMOS?
Logic will be 0 at N1 and 2
Input.
and
Always remember gate input.
yes, sir.
Gate input. Always remember. Okay, so let us try to design the AND gate using NMOS. So we have to connect the transistors in series. So how we can connect in series? Let us see here. Just you need to understand how to connect the transistor in series and parallel. After that, you can definitely draw, because it's very easy. Just you have to correlate with the switch only. Then after that, definitely you can. So here, this is A and B, and here let us say this is E, and you will get output from here, no problem, anywhere. This is just for the example here. Okay, now this is for using NMOS, right? And gate using NMOS. So if you want to design the A, B, sorry, gate signal will be N1, N2. Okay. So it will be N1. If I am if I am wrong somewhere, then you should remind me. You should correct me. Okay. So now here it will be N1 and N2. This is AND gate using PMOS. Okay. Now you can guess what will happen here. Let us say the configuration, that is A, B, and let us say this is NMOS 1, and similarly for NMOS 2. So here NMOS 1 and NMOS 2 and the output. Okay, let us say here 0 0 0 1 1 0 and 1 1. What will happen to the NMOS 1 and NMOS 2?
Sir,
For
I guess the inputs will be on gate terminal.
no. Gate we can design in such a way that because we can design the logic gates in any way. So here we are fixing the gate terminal that is at logic 1, and we are varying the VDD and VSS here.
Okay, sir.
Okay,
And output will be taken on which terminal, sir?
I will let you know. I will let you know. Just for the example, for the switch, I am telling how to design the AND gate, OR gate like that. So let us say here, if the input, let us say this is N1 and N2. Here, let us assume for NMOS, N1 and N2 are at logic 1. Okay. So what will happen if A is equal to 0 and B is equal to 0? If both the input terminals, if the input terminals for the NMOS and NMOS 2 are 0, then what will happen? It will be off, right? Off. Okay. 0 and 1. So 0 and 1 means what will happen? This will be off, and 1 is B. B is 1. So it will be on. So here it will be off, and this will be on. 1 0. 1 0 means transistor 1 will be on. It will be on, and here it will be off. But for 1 1, all transistors will be on. But what will be the output in this case? If the both transistors will be off, then let us say, okay, for the both transistors will be off, then definitely it will be at logic 0. No problem. Okay, let us say A is equal to 1 and B is equal to 0, then in that case, NMOS will be turned on and NMOS 2 will be off. So the circuit will be incomplete. Let us say the switch is connected in this way and in this way. Let us say this is S1 and S2. This is open, this is closed. Let us say this is closed and this is open, right? And we are interested in finding the output. So what will be the overall output here? If the switch 1 is closed and switch S2 is open, then you will get the current in the output.
Zero current.
Zero
Logic
current.
zero.
Yes, zero current, right? Logic 0. What will happen if the condition will be reversed? That is, here it is open. Let us say this is open and here this is closed. Then what will be the output? Current through flow through this branch?
Zero and logic will be zero.
Yes, 0. Let us say logic 0. If the both switches will be closed, then in that case only you will get the current flowing through this branch, right? So it will be at logic, let us say this will be at
1.
logic 1. So through the switch configuration only, this circuit only, we can realize, if I will ask you to design any logic gates, then you can design using these 3 circuits. Okay, so let us move towards the NAND gate and NOR gate. Okay, so what will be the conditions for these circuits? What will be the assumptions? What will be the necessary conditions here? For PMOS AND gate using PMOS, what will be the conditions for N1 and N2?
At logic 0.
Must be at logic 0. Let us move for the 2 input CMOS NOR gate. Oh no, sorry, AND gate first, then we will discuss about. Okay. NAND gate using CMOS. Okay, so first let us try to understand what will be the Boolean expressions for not 2 input, right? 2 inputs only. because similarly you can design for the 3 inputs, 4 inputs. So what will be the Boolean expressions for the NAND gate? Anyone remember? Let us say Y is the output and A and B are the inputs. So what are the Boolean expressions?
A dot B bar.
A dot B bar, right? So which will be equal to A bar plus
B
B
bar.
bar. So using these equations, we can design how the symbol of the NAND gate will be like that. Let us say A is the input and B are the inputs, and here output, let us say this is Y, right? So it will be equal to AB bar. So using these expressions, if we are interested in writing the symbol using these equations, that is A bar plus B bar, then we will have to write in this way. Oh, sorry. Using the OR gate symbol. So here we will have to use the bubbled input. This is known as the bubbled input. A, B, and this is Y. So in the output you will get A bar plus B bar. If you don't want to use the bubbled input, then we will have to connect the circuit in such a way that let us say this is A, B, and in the output you will get A bar plus B bar. So do you understand the meaning of these things? What is this?
Not get.
Not get, right?
Inverted.
Yeah, inverter, you can say. So, okay. So if you know this basics, okay, just talk about the truth table. So let us say this is A, B, and Y. So 0, 0, 0, 1, 1, 0, and 1, 1. So here the output will be 0. Ah, sorry.
Sir,
Wrong.
1.
Yes. Sorry. So it will be 1, 1, 1, and 0, right? Okay.
Yes, sir.
So now the design consideration. How can we design? So we know very well, here we need, if you see the operations or expressions, that is this one, then you can realize that we need, this is a combination of AND gate, right? Y is equal to AND gate, and also you can say OR gate. That is true. We can design this NAND gate using AND gate also or using OR gate also. That is true. If you see the symbol, this is a symbol for inverted AND gate, and this is a symbol for inverted OR gate. So we can design the circuit by using AND gate and NOR gate, AND gate and OR gate. So what are the conditions? Let us say, what are the conditions for the AND gate? How can we design the AND gate using CMOS transistors? Yes? How can you design the AND gate using the CMOS?
So transistors in series.
Series, right? And for the OR gate, it should be in parallel, right? Okay. So to design the NAND gate using CMOS, let us see the configurations. We will have to connect, because here we are, if you see the expression unit 1, then this is the OR gate and this is for the AND gate. So see here how the configuration will look like that. Here we will change the input and output. So let us say for AND gate we know, for OR gate we know very well, we need to connect the transistors in parallel. Okay. So this is in parallel. So now again here we will have to connect two transistors in series, and we will understand the operations. So this, okay, so here, okay, this is 0, or you can say ground, or you can say VSS, and here you can consider this is at logic 1, or you can say VDD, and here there are the inputs, that is A, B, A and B, and here you are taking the output. So if you see the configurations, then there are two configurations here, that is series and parallel both. So the first pull up, this is the pull up sub circuit. The first upper circuit is known as, this is known as the sorry, I will let you know the operation so that you can understand. Pull up sub circuit. Okay, and this one is known as the pull down sub circuit. So if in the exam, if I ask you for the 2-input NAND gate, what will be the number of transistors required to design the pull down sub circuit, then your answer should be 2, right?
Yes, sir.
What about the 3 inputs? How many transistors are required to design for the 3-input pull down sub circuit? It will be 3, right?
3.
3. Okay. So you have to take care of the configurations that to design the pull up sub circuit, we need to choose the PMOS, right? This is PMOS. And if you see the circuit, this is NMOS. Okay. So how it will be responsible, how we can understand the output. Let us see, this is NAND gate, right? So NAND gate, we know very well that here, what is called the truth table. Let us say we already supplied the VDD at logic 1. Okay, this is fixed. This is not going to change. Now, what will happen to the transistor if the A and B are 0, 0? So what do you think about the transistor? It will be turned on or it will be turned off?
Turn on.
Turn
Turn
on,
on.
right? So turn on means you will get the signal in the output, right? Because
Yes, sir.
both the transistors are turned on. Okay, good. What will happen if, let us say this is off? Let us say this is, okay, Q1, Q2, and here say this is, okay, NQ1 and NQ2. Let us say this is PQ1 and PQ2. Here, where the Q represents the transistors. Q represents the MOS transistor. MOS transistor. So let us say, if let us say Q1 is off and Q2 is on, then what will happen in that case to the output?
Output will be still high.
It's still high, right? Means it is at logic 1. Similarly, let us say Q1 is high and Q2 is at logic 1 and Q2 is 0. Then in that case also you will get
Logic 1.
logic 1. What will happen if the signal A and B both are 0, 0? Sorry, both are 1, 1.
Then output will be a little bit upper pull up part will not give, will be off in off
Yes.
state.
And what will happen? So in that case, this transistor will act as if both the inputs are 1, that is at logic 1, then this pull down sub circuit will act as a wire. Okay, as we have seen in case of inverter circuit. So if it will act as a wire, then what will the voltage drop across that wire?
No voltage drop.
No voltage drop. Means
Sir,
it will be
the
0,
voltage
right?
Sir,
will be
complete
same.
zero.
Yeah, it will be 0, right? So it means that you will get output voltage
0.
0. So then you can ask me for the 3 configurations, that is for the 3 sets. Let us say this one. For the 3 sets, the pull of transistors, the pull off, that is, if you see the configurations, then you can see that this for 3 configurations, that is, oh, for these 3, pull-up sub-circuits are responsible. Sub-circuits are responsible, right? But when both the inputs are at logic 1, then we need the pull down sub-circuit. Okay, so that's why the pull down sub-circuit is made of a series combination of, okay, so if you see the pull up sub-circuits, which are connected in parallel, and pull down sub-circuit are connected in series. So here you can say that the pull down sub-circuit is made up of a series combination of 2 NMOS transistors. These are responsible for conducting logic 0 to the output node when both of the gates are at logic 1. However, the pull up path on the other hand consists of a parallel combination of 2 PMOS transistors. If either of the gate is at logic 0, the output node assumes the value 1, that is at logic 1, right? So any difficulty in understanding the NAND gate using CMOS?
No, sir.
Okay, so let us move for the NAND gate. Sorry, what is remaining? NOR gate, right? Okay, NOR gate. So just we have to reverse the operations. Okay, so NAND gate, reverse the circuit diagram, then you can get reverse. Means what is, okay, first talk about the NOR gate. For the 2 input, let us say 2 input. Okay, so what were the Boolean expressions? Anyone remember? Yes?
A plus B bar.
Y is equal to A plus B bar, right? So you can write
A bar dot B bar.
Oh, that is fine, good. So here, so based on this, what will be the symbol? That is, symbol will be like that. Let us say this is A, here B, and Y. This is equal to A plus B bar. But using this symbol, you can design using AND gate. But here for the AND gate, the input must be bubbled input. So which is equal to A dot B bar, or you can also design in this way, that is, I think you all have studied in detail, I guess, about the logic gates, right? In 3rd semester or maybe in basic electronics.
Yes, sir.
Right. Okay. So now, what will be the configurations? So if you see previous circuit, here we are connecting the pool of transistors, which transistors are connected in parallel, right? And pulled out consists of transistors which are connected in series. Now just we have to reverse operations, right? Because NOR and NAND are opposite each other. So okay, let us start with the truth table first. Then you can understand truth table. So truth table means okay, A, B, and Y. Let us say 0, 0, 0, 1, 1, 0, and 1, 1. So what would be the output here for NOR gate? Yes. By using truth table, you can design the circuits. So just to understand. So what will be the output for 0, 0? It will be 1.
So 1.
1. For remaining, it will be 0, right? True?
Yes, sir.
Okay. So by using the truth table only, we can design. Okay. For 0, 0, you are getting 1. So what does it mean? It means that if the upper, that is pull-up sub-circuit, will be made up of PMOS, but it will be connected in series, right? For series, what we know, both the terminals will be, both the switches will be closed so that you can get output. That is true or not? If you see, again, I am drawing. Wait, let us see. Okay, here you can see the switch. Let us say this is S1 and this is S2. So let us talk about the PMOS. Let us consider this is PMOS, okay? This is PMOS. This switch has been made using PMOS. So for 0, 0, 0, 0 means what will happen? Let us say here you are getting the output. Okay, now you can understand. If let us say switch S1 is open, means you are applying 0 logic. Here you are applying the 0 logics. Then what will happen to PMOS? It will on, right? Then you will get some current or voltage, you can say, in the output. That is true?
Yes.
Logic 1.
Logic 1, right? Okay. But for the remaining case, what will happen? That is either it will be 1 or 0, 0, 1, 1, 1. Then it will be turned off, right?
Yes, sir.
Okay. So let us try to understand. It's just using the truth table, you can design the circuit. Okay. So it means that here the pull-up transistors, pull-up sub-circuit must be designed in, must be connected in a series. Okay. So just try to, okay. So using, because 0, 0, for 0, 0 we are getting output at logic 1, it means that we will have to connect both the transistors, that is PMOS transistors, in series. So in this way you can understand. Okay, so let us say this is A, B, and here you are getting the output. So now pull down transistors will be made up of parallel using NMOS. And one thing I would like to see, if I am providing you notes, it doesn't mean that you will not watch the video, because I'm not writing most of the things here. So you need to watch video so that you can understand in detail. So let us say this is at logic 0, that is, you can say VSS. VSS means ground, always say ground. And here let us say this is at logic 1, or you can say VDD. So here again, we will have to highlight the sections, that is for pull up and pull down. So this is the pull up subcircuit, and lower one is known as the this is the pull down. Pull down subcircuit. Okay. So now we need to understand the operations. Okay, so let us say both the inputs, that is A and B, are at logic 0. Then what will happen in that case to this? Let us say this is PQ1 and PQ2, and this is the NQ1 and NQ2, where Q represents the transistors, MOS transistors. So what will happen if the both the input terminals, that is gate, that is A and B, are at logic 0? So what will happen to this transistors, P transistors, PMOS transistors? It will be off, right? So you will not get any. Okay, it will be at logic 0, then it will be operate, right? For 0, 0, the transistors will be on. So you will get the output. What will happen to the remaining cases? If let us say this is at logic 0 and this is at logic 1. So it will be turned on, but it will be turned off. Then in that case, the circuit will not complete and you will not get any signal with the output. That is, the output will be at logic 0. What will happen if let us say this is 1 and this is 0? Then in that case, what will happen? Again, you will get the 0 in the output. Okay. So these are the operations. So the pull-up subcircuit is made up of a series combination of two PMOS transistors. These are responsible for conducting logic 1 to the output node when the both of the gates are at logic 0. However, the pull-down path, on the other hand, consists of a parallel combination of two NMOS transistors. If either of the input is at logic 1, then in that case, the output node assume logic 0. Okay. So in any difficulty in understanding the NOR gate using the CMOS transistors?
No, sir.
Okay. So based on the above fundamentals, if I will give you one example, so let us say implement the Boolean function z is equal to a plus b multiplied by c plus d whole bar using CMOS transistors. Just give me 5 minutes. CMOS transistors. Okay. So first, what we need to understand? First, we need to understand that here, how many inputs are there? If you see the expressions, there is a Boolean function, then what can you conclude from there? How many inputs are there?
4 inputs.
4 inputs. Very good. So here, 4 inputs. Right? Okay. If you again see the expression, that is z is equal to a plus b multiplied by c plus d, then you can conclude that this is OR gate, right? This is also OR gate, right? So the first OR gate will be 2 input, that is A and B. Second one is also the 2 input OR gate. So we can design, okay, let us say here A, B. Here second OR gate, that is C and D. So what will be the output here? A plus B, right? Here it will be C plus D. Okay. Now we need the product, right? A plus B multiplied by C plus D. So for multiplication, which type of logic gates we need to select? Yes?
And
AND gate. Very good. AND gate. But if you see the Boolean function here, then there is a bar on the multiplication. So for bar, we need to select NAND gate. So here it will be NAND gate. So this will be the expression, that is finally you will get A plus B multiplied by C plus D the whole bar, right? Now for OR gate, let us say this is the first OR gate, second OR gate. So first OR gate, this is 2 input, right? So for the 2 input, how can we design the first OR gate using the CMOS? The CMOS should be connected in, yes, in parallel, right? For OR gate, we connect the we connect the transistors in parallel. Okay. And for the AND gate,
series.
So here, based on the above fundamentals, we will connect. So this is the 4 input, right? So 4 inputs are required. So how can we design? Let us see here. So we need to connect. Transistor should be in connected in
Parallel.
2 parallel. So this will be PMOS here. So this will be, let us say this is A and B. So this is for the first OR gate. What will be the case for the second OR gate? Similarly, we will draw the transistors A, B. C and D. Okay. Now it has been completed. But for the AND gate, because we also need AND gate, so what will happen? What will be the case? Or VDD. So what will be the configurations now to get the NAND gate? This is NAND gate, right? So we have already drawn the circuit for this 4 input OR gate. What was the NAND gate? We will have to connect the switches in series or parallel?
Series.
Series. But if you break this equations, then what will be the case? Right? In this way we can write. Any doubt?
No, sir.
No, right? So again, if you see for these operations, because let us say this is the first term and second term, then we need to connect in parallel. But because of the AND operation, this is AND, so we will need, okay, you can understand. Okay, let us see here. So what will be the, now we need to connect okay, so this will be B. And here, what will be the voltage? And you are getting the output here first. Okay. So what will be the voltage here? It will be at logic 0, or you can say VSS, that is grounded. So for the two OR gate, we have to design, or you have to connect the transistor in such a way that like this. So if you try to identify this part, this is for the, so two input OR gate. Okay, now this is the first case. What about the lower part? So lower part, you can see in the output, we need to connect the switches in series, because if you, this is the OR gate and this is the NAND gate, inverted AND gate, you can say. You can, this is also known as the inverted AND gate. So for AND gate, we know very well, we need to connect the switches, or you can say transistors, in series. So here, if you see the expressions, final output expressions, then you can see here A plus B ka bar in addition with the C plus D ka bar. So A plus B, again this is OR gate, right? Again this is OR gate, but inverted OR gate. So that's why this is the third part, third. So you can say here, this will get at this one, and this is the fourth, so you can get C plus D bar. So any difficulty here?
Sir, in the pull-up part, sir,
No,
the
here pull up part means here you can see.
sir,
this
I
is-
have a doubt in that part.
Okay, you can say.
Sir,
Yes.
in the branch which is having transistor A and C, I think so. It should be A and B.
You are thinking it should be A and B.
Sir, if we consider the logics at terminal A B C D as
Okay,
1
yes,
0
yes,
1
yes,
0.
yes. Okay, wait. Let me. Okay. Thank you so much. How can I erase? Okay, it should be B here, right? And here it should be C and D.
Yes, sir.
B, and it should be C, right? That is correct now?
Yes, sir.
Okay. So remaining part, any doubt?
No, sir.
Okay. So I have to save. So in this way, today we have finished the unit 1.